So in the last class, we discussed about LS coupling. LS coupling for non-equivalent electrons. We considered a single electron case and two non-equivalent electrons. Non-equivalent means they are having different L values. Okay, so that what we discussed last class along with that modular factor. So we continue from that LS coupling, and today we will discuss about for the case of for two equivalent electrons. So if you're having two equivalent electrons, what will how we'll calculate those LS coupling? That we will discuss today. So if you're having two equivalent electrons means that they are in the same orbit. For example, P2. Okay. So P2 means two electrons in that P orbit. If you consider that, you can have two electrons in the same orbit. It can be up or down, depends on spin. Okay, it can be up or down. So there are two electrons in the same P. So that is why it is called as equivalent electrons. Now, if you consider this kind of scenario, then we have to use some different scheme to calculate the LS coupling or corresponding spectral terms and all those things. The scheme is called Breit scheme. Breit scheme. And in this Breit scheme, we have to arrange those ML values. So first we consider this P2 itself. So if you consider P2, we have two electrons. Okay. So the L values are for first electron it is 1, second electron also it is 1 because it is in the orbit. And S value it can be half, plus half or minus half, depends on the state. So we'll take the magnitude smallest as half, it's 1. Okay. And now if you consider the Breit scheme, we have if L equal to 1, that I will write L1. This is S1, S2 for second and first electrons. So this is L1 for first electron, this is L2 for second electron. So ML1 will be equal to minus L2 plus L, so minus 1, 0, plus 1. And ML2 will be equal to minus 1, 0, plus 1, because it should be added from minus L2 plus L. Now in Breit scheme, we have to make some matrix or some a set, okay, to find out the corresponding L values. So this scheme is like this. First, you have to form set of values for ML. So we'll write ML1 here, plus 1, 0, minus 1. Then in this is in this row, and in this column we write the second ML values, ML2, plus 1, 0, and minus 1. Now add these two ML values, so plus 1 and plus 1 will be 2, 0 and plus 1 will be 1, minus 1 plus 1 will be 2, and plus 1 plus 0, that is 1, 0 plus 0, 0, minus 1, 0, minus 1, then plus 1 minus 1, that is 0, 0 plus minus 1 minus 1, 0, sorry, minus 1, plus minus 1, that is minus 2. So this is a set of values for capital M, capital L. Okay. This is ML1, this is ML2, this is the total ML value, that is capital. Okay. So this is smaller M and capital. So these are the values which are possible for the resultant L. Okay. So now if you consider that S values, let's consider S values. We have S1 is equal to half, S2 is equal to half. So total S, capital S will be equal to S1 plus S2 to S1 minus S2. So this will give you S1 plus S2 will be nothing but 1, is half plus half. In the next case, we have half minus half. So that will give me 1 and 0. Okay, so S values are 2 also. So 1 and 0 will be answer. So if you consider that S equal to 1, if you consider S equal to 1, which means that both electrons having same spin, okay. So by Pauli's exclusion principle, Pauli's exclusion principle, they should differ, in their ML values. Yeah, because they are having same L value, same spin, same N also. So they should differ these ML values. Not two electrons should have all those common numbers which are equal. So if they are having same L value, same spin, and same N, then they should differ in their ML values. ML value should be different. Okay, for this case, when S is equal to 1. Okay. Now, if you consider S equal to 0, S equal to 0, which means that both are having different spin or opposite spin, you can say. Hence, any ML values are possible. So if you consider that scenario, let's put that scenario here. For if you consider if S equal to 1, okay, then their ML should not be equal. So we can choose different ML values from this set. Okay. So first, let's say I have taken this set. For any set, I will take this set of values. Consider this set. So we have different ML values. But if you consider here, this case, the total capital small, this ML capital ML value, which is 2, that is resultant ML value is 2, that is having same ML1 and ML2 values, which means that both electrons are having same ML values when you take this as your resultant. Okay. Similarly, if you consider this one, okay, that is having ML1 for first electron, ML value is 0. Second electron in ML value is +1, so it is not a problem. And if you consider here also, first electron is having -1. If you take this one, first electron is having -1 as your ML value, second electron is +1, so they are different. That is also possible. This one, if you take, then it is -1 and 0, no problem. But when you consider this one, -2, which is having, if you consider -2 as your resultant ML value, then it is having both ML1 and ML2, which are same. Okay, so that is not possible because if you consider this one, sorry, this one and this one, they are having same ML1 ML values for both those electrons. That is not allowed when S equal to 1. Okay, so this set is not allowed for s equal to 1. Now I will take another set like this. So in this case, what will happen? If you consider this plus 1, okay, so if you consider this as your resultant ml value, this 1, this as your resultant ml value, then that is having plus 1 ml1, that is for first electron it is plus 1, and for second electron it is 0. Okay. So that is allowed. If you consider this one, ml1, first electron is having plus 1, second electron is having minus 1. This one you take first electron is having 0, second. So in this set, 1, 0, minus 1, 1, 0, minus 1, all those ml1, ml2 values which are different for those two electrons, they are having different ml values. For s equal to 1, this set is allowed. So ml values equal to 1, 0, minus 1 is allowed, which implies L capital L which is equal to 1. Okay. Capital L equal to 1, corresponding ml will be 0 minus 1. Now if you consider this value 0, 1, that 0 also having same ml value, ml1 and ml2, so that is not allowed under this condition. But if you consider when your s equal to 0, if s equal to 0, then the other ml values are possible, because when s equal to 0, both are having different spin. So all ml values are allowed because spin is different. So not all quantum numbers are same. Spin is different. So any ml values are possible. So if you consider that case, then this set 2, 1, 0, 1 minus 2, that is possible in this case, because ml value you can take any value for both electrons, and that will give me L equal to 2, and another set which is 0, ml equal to 0 is possible, that will give me. So what is this? L equal to 1 means this is P state, this is in this D, and this is S. Yeah. But under this condition, that is S equal to 1, we have this L value. So that will give me the multiplicity for this. See, multiplicity equal to 2s plus 1. That will be, in this particular case, it will be 3. And here we have multiplicity equal to 2s plus 1 equal to 4. So in this case, I will have multiplicity which is equal to 3. And here we have multiplicity is equal to. Okay. Now, if you consider J values, consider J values. So considering that J values we have in this particular case, what will be that J? J can be L plus S to L minus S. So that will give me the J values as L is 1 here, S is 1. So L plus S is 2, 2, L minus S, that is 0. So that will give me the values as 2, 1, 2 to 0 in steps of 1. Okay, so 2, 1, 0. Now if you consider this case, J value will be L plus S to L minus S. That will be in this case 2 plus 0. So 2, 2, 2 minus 0, 2. So that will give me J value is only 2. And in this case also J equal to L plus S, that is 0 plus 0. So 0 plus 0 is 0, 0 to 0 minus 0 is also 0. So this, okay. So the total terms will be from this set I can write for 3p, 3p, I have terms, spectral terms, spectroscopic term. That is 3p, JSR 2, 1, 0, the first term. And then I have, this is singlet case. So this S equal to 0 called as singlet, and S equal to 1 is called as triplet. You can see that this is multiplicity is 1. That's why it's called as singlet. This is in this case it is multiplicity is 3, so it is triplet. Okay. So this one is triplet, and this two are singlet. So in this case I have 1, B, 2, then 1, S, 3. So these are the spectral term corresponds to P2. And I should mention one more thing here, that if you're having some spectral term are associated with NLQ, okay, that means the terms of the configuration NL power Q are the same as the term NL R minus Q, where R is the maximum number of electrons. So what that means is that if you're considering this P2, P2 is having this spectral term. So I'm writing it as P2 with some N, 2 P2, 3 P2, or any P2. So let's take it as 2 P2 in this particular case, or N equal to 2, for example. And that will give me these terms, 3P210, then 1B2, 0. So these are the terms corresponds to this 2P2 state. Now, if you want to find out 2P4, this also this particular configuration will have the terms, spectroscopy term, same as that of P210. That's in p orbit. The maximum electrons will be equal to 6. Maximum number of electrons that you can feel in that p orbit is 6. So whatever, if you consider p2, whatever configuration corresponds to this p2 will be same as that of p6 minus 2. That is nothing but p4. So these two will be having same spectral terms, because under this, if you want to calculate, you can calculate by using the conventional method. But this one, you remember, then you can write it. If P2 is having these, P2 is having these terms, spectral terms, then P4 will be also have the same spectral term. Okay. Similarly, if you consider any other states, for example, in this kind of states D, if you consider D3 and D7, they are having same spectral term because maximum is 10 for D orbit. So D3, whatever spectral term corresponds to this D3 will be same as that of D7. Okay? And if you consider any other example, for example, S1 and S2, then we have F, which is having 14, so you can take 4 and 10 or whatever it is. So they will be having same spectral term. That is NLQ and NLR minus Q will be having same spectral term. Okay, the Q is nothing but that number of electrons. Okay? Now, if you consider further, there are some other important points in these spectral terms. Suppose if you consider half-filled state, in the case of half-filled, what will happen? Because both of them should have the same ML values, right? So in this particular scenario, if you're having half-filled, then I will talk about first closed subshell, such as closed subshell, such as S2, P6, P10, F14. They are filled, completely filled. In such cases, they have a spectral term. Their spectral term always end up with 1s. This is the only spectral term associated with this loss subshells. S2, P6, completely filled subshells. Okay. Why? Because they are having the maximum number of electrons. Closed subshell will be having maximum number of electrons. For them, L will be equal to 0. So in this case, for all those states, you are having completely filled subshells. Then they will be having L equal to 0, S equal to 0, J equal to 0. Since they are completely if you consider that total values. Okay. Then the second one that we already discussed, so that N, we are having NLQ and NLR minus Q. They will also have same spectral term. They will be sharing same spectral term. Okay. So half also you can get that. Now, if you consider the order of terms and find structure, order of terms, these are some important points that you have to understand. So order of terms, if you consider, okay, the largest multiplicity lies lowest. When the largest multiplicity lies lowest. And second point is that if you are having multiplicity same, then the largest L value lies lowest. And if both are having same L values, then with equivalent electrons in a less than half-filled subshell, the level with lowest J value will be lost. Okay? If you are having equivalent electrons or equivalent electrons, means that they are having same L values. So for equivalent electrons with less than half filled, they are not half filled, then they will be having the, in this particular case, then the lowest J value, lies, that means terms with lowest J value lies lowest, and the same scenario for equivalent electrons with more than half filled, then lowest J, so this is highest J lies highest J lies lowest. Okay, then if you consider term with half filled, okay, these are more than half filled and less than half filled. Okay, so if they are half filled, if half filled, then very the less fine structure speaking. So these are half filled terms. Terms half filled shows very less fine structure splitting, fine structure splitting. And then so we can say the lowest terms arising from the half filled subshell are the S term and are uh, very stable. They are specially stable. So terms coming from this half filled terms arising from half filled, so they are having subshells, half filled subshells. They are having S term. This will be S terms. So which means that any uh, shell of any subshell which is filled half filled, then they will be end up in this S term. So if you consider that 2S, so this is S case, if you consider S1, that is half filled S state. So this will be having 2S half term. And if you consider P with 3, okay, so that is half filled, and that will be having 4S 3 by 2. And if you consider The other one is D5 will be having 3, 4, 6 S pi by 2. And if you consider F, that is with 7, that will be having spectral term 8 S 7 by 2, and so on. Okay. So those are having with half-filled number of electrons which are half-filled. So then corresponding terms will be like this. Okay. For S, if it is S, then 2s1 by 2. If it is P3, then it is 4s1 3 by 2. D5, that is 6s 5 by 2. Just remember this 1 by 2, 3 by 2, 5 by 2, and 7 by 2. Whatever it is coming here, multiply that with 2 plus 1. So this is, in this case, you can get this value as 2j plus 1. This is actually 2s plus 1. In this case, you can get this as 2j plus 1. Is this, if you multiply 2 with r plus 1. Okay. So these are the terms corresponds to this particular case when you are having that half. And if you consider the selection rule for this LS coupling, selection rule for LS coupling. For the selection rule, we can say that for single electron transition, so selection rule means that after splitting into different lines, so in this particular, after this LS coupling, there will be transition between those states. Okay. So in that case, the electron has to move from some state, higher state to the lower state, and those transitions are controlled by some rules. Those are called as selection rules. And in this particular case, after LS coupling, from which state to which state the electrons can go, that is also restricted. That rule is given by, for if you consider for single electron transition from one particular state to the other state, then that should follow delta L, which should be equal to plus or minus 1. And for 2 electrons, for the case of your 2 electrons transition, then we have 2 L values. First one delta L1, that should be the same, plus or minus 1. But the second electron, delta L2, can take values 0, plus or minus 1. So this is plus or minus 2. Now, if you consider this is for electron, single electron and 2 electron cases, and there is no restriction. There is no restriction on n value, so n can vary any values. So there is no restriction for that. And for atom as a whole, we consider for atom as a whole, that should that means that if you consider the atoms as a whole, okay, complete atom if you consider, then L, S, and J must change as L, S, and J. J must change as in this particular case delta L, capital L. So delta L, capital L, we have to consider, that whole item. Then all L1 plus L2, all those values will come. So cap delta L, that is changing that capital value of L, that should be 0 plus 1. Okay. And delta S equal to 0, and delta J equal to 0, plus or minus 1. And in this case, delta L equal to 0 plus or minus 1. And in this particular case, if it is single electron transition, then delta L equal to 0 is allowed. Similarly, if you consider this state, J equal to 0, J equal to 0 to J equal to 0 transition is not allowed. So even delta J equal to 0, then you can take J 0 to J0. That is not possible. That is not allowed. It is forbidden. J equal to 1 to J equal to 1, that is possible. Then 1 minus 1 will be delta J equal to 0. But J equal to 0 to J equal to 0 also will give you delta J equal to 0, but it is not possible. It is not allowed. It is not allowed. Okay. So these are the important points regarding PLS coupling. So what are these transition? I will just tell you that this transition means I will check. Okay. So in this 2p2 state, I'm getting different states. So this p2, I'm having one energy level, okay, before LS coupling, or with a definite L and S values. But here, when you have that LS coupling, after LS coupling, we have three different states. S0, in this case, we can see S, D, P. Three different states are formed because of LS coupling. So if you consider these states, so this single energy level splits into three here. Then we have to consider which one will come lowest, which one will come the highest. So in that case, we have to first consider the multiplicity, which one is having largest multiplicity. So in this case, this is having the largest multiplicity. So that one should come the lowest. So that 3p2, that should come lowest. And in that, which one will come down, which will come up? The greatest, if multiplicities are same, then we have to consider the greatest L value. But in this particular case, we have same L values for different these J values. So then next is that if this orbit, P orbit is less than half filled, then we have to take the lowest J value as the lowest. If it is more than half filled, then we have to take highest J value as lowest. So in this case, we have less than half filled. P is having 2 electron, which is less than 3. So it is less than half filled. So first, for this case, first we have to take the lowest one, which is nothing but that P3, okay, because multiplicity is maximum for that. Now this P3 again splits into the three different J values. So I will take that. Okay, so which one will come down? Since it is less than half filled, so 3p less J will come down. 3p0, 3p1, and 3p2. This is for equivalent electron case. Okay. Now the next one is 1D2, right? So it is having only one. So we have to consider which one is having the highest multiplicity from these two now. So they are having same multiplicity. So then we have to look which one is having highest large, the highest L value. So this one is having the largest L value. Then this should come lowest. Okay, so then I draw that. And this is nothing but 1D2. Then at the top we have that S. This one is 1. Now there can be transition which can happen. There can be transition happening between these energy levels. So suppose this, there is one electron which is coming from 1s0 to this 1d2. Then we have to consider that selection rule. First one is that total, if you consider delta, if you consider total atom as a whole, that is delta L equal to 0 or plus or minus 1. Okay, so for single electron transition, we should not take that delta L equal to 0. But here we have two electrons in this particular state. So we have delta L equal to 0, delta L equal to plus or minus 1. So in this particular transition, you check what is that value, delta L. Delta L is here we have S L equal to 0. Here D we having L equal to 2. So the delta L value is delta L value here is 2 minus 0 is 2. So this transition which is not allowed because delta L value is not 0 plus or minus 1. So this is not allowed. Okay, consider another one. Let's say let's take these two transition. 1D2 to 3P2. So L equal to 2 here, L equal to 1. So delta L equal to 1, 2 plus 1, 2 minus 1 is 1. So that will give me, here we can take this. So this will come plus 1 and this will be allowed because delta L is plus 1. For delta L it is allowed. If you consider delta S, capital S, what will be that? It should be equal to 0. That is not valid here because here we have capital S value which is 0. Here we have capital S value which is 1. Okay, so then this is not again allowed. Consider another transition. Let's say this one. So this is also not possible because multiplicities are different, which means that those transitions are not possible because delta S should be equal to 0. And if you consider this transition, let's say this one. This transition, we have delta L, if we consider this one, these two, delta L, that is equal to 0. So that is allowed. Then we have delta L, delta S, if you consider that is also equal to 0 because same multiplicity, S value is 1 here. Here S values are different. Sorry. I got this because here we will be having S value which is equal to 1 here, right? Sorry, S value equal to 0 here, S value equal to 1. So this will be allowed in that case. Sorry about that. So just so sorry about this. So we have a state here, which is this. And if you take transition from here to here, it is okay because we have delta L between these two. Delta L is equal to plus 1. And if you consider delta S also, delta S that is also plus 1. Sorry, delta S S equal to 0 here, S equal to 1, so this is equal to 1, right? So this is not allowed. Okay, so this is not allowed because delta S will become 1 here because here S is equal to 0, here S is equal to 1. So this is delta S equal to 1. So considering these two, is this two delta L equal to 0 and delta S equal to 0. Then we have a delta J, we have to consider solution rule. Delta J should be equal to 0 or plus or minus 1. So delta J, if we consider 2 minus 1 here, there is 2 here, here it is 1. So 2 minus 1 is 1. So delta J equal to plus 1. So all are okay. So this transition is allowed. This one is allowed. So this is how we check whether the transition is allowed or not by using that selection. That's selection rules. Now this LS coupling scheme is only applicable when your atom is very small. But if you're having more number of electrons in your atom, then the instead of LS coupling, the electrons in the same orbit couples together with those L and S values. Then we have another coupling scheme called as JJ coupling. So let's consider this case. We have an atom like this is having 2 electrons, and another atom. Let's consider here is a little more larger atom. So we consider this first orbit, this second orbit. So we have electron, 2 electrons, say 2 number of valence electron here. Here we have 2 electrons in the orbit. So if we consider this scenario, then we have the L values for first electron. If you consider LS coupling, LS scheme, what we have to do? We have to consider L value. First, I will consider L star, that is magnitude value. So L star will be equal to L1 star plus L2 star for these electrons. One, suppose this is the first electron, E1 and E2. This is the for this. We have to consider the outermost electrons. Okay. So L star equal to L1 star plus L2 star. Similarly, S star is S1 star plus star. I'm talking about that magnitudes. Okay, so if you consider that J star magnitude, that will be L star plus S star. So in terms of total J, then I have to write J equal to L plus S to L minus S. In the case of LS coupling. So what is that? Your L1 will be equal to 1. For example, if you consider example, P orbit, we consider P1. Sorry, here we need 2. So let's consider it as P2. Or we can consider P1 itself. Talking about this one. So this is the LS coupling we have to do for the case of light atoms. So suppose there is only one electron in the P orbit, then we can have L1 equal to 1. Okay. And correspondingly, S will be having half. Then we have to calculate L plus S and assume that value function. Okay. If there are 2 electrons, then we have to consider the L and S value of both those electrons, as in this figure here. In that case, you have to calculate total L value first, L1 plus L2. S value S1 plus S2, and you add both of those values to get this J, or in the vector form you can have that total J equal to L plus S to L minus S. So first you have to calculate capital L from all those L1, L2, L3 small for corresponding to those electrons. And then you have to calculate what is the capital S after calculating small s1, s2, s3 for all those electrons. Then all those values you have to calculate. Then add L and S. Then we get J. But in the case of heavy atoms, in that case we have a different scenario. We have outermost two electrons, as you can see from this model. Then in this particular case, first what will happen is that the spin orbit coupling of each electrons is larger than this orbit coupling or spin interaction. In this particular scenario, if your atom is larger, number of electrons or the size of the atom is large, then the interaction, that is spin orbit coupling of each electrons is stronger than the orbital and spin interaction. So what is happening here? We have L1 for this, L1 for this. So these two L1 first interact each other for different electrons. What are these L values? They will interact, and we'll get capital L. And similarly, we have S1 and S2. This S1 and S2 will interact, and we get capital S. Okay, then we couple these two. But in this case, when your atom is having a heavy size, then what will happen is that this L1, there will be L1 for this. This is having L2, and this is also having S1, and this is having S2. Instead of coupling between this L1 and L2, or interacting with L1 and L2, this L1 will couple first with this S1. That is for the same electron. Both L and S will couple first, and this second electron also, this L2 and S2 will interact each other, and these two will form J2. This two will form J1, and these two J1 and J2 will interact to form the second J. Okay. So in this case, the coupling of the spin orbit coupling of each electron, will be stronger as compared to the orbital and spin interaction of the different electrons. Okay. So for example, if you consider p states, let's consider 2p1 case. So 2p1 state, if you consider for JJ coupling, then we have L1, which is equal to 1, S1 equal to half. Okay. So J1 will be equal to L1 plus or minus S1. That will give me 1 plus or minus half. Okay, that will give me 1 plus 3 by 2. 1 plus or minus half, 3 by 2. Now, if you consider for D electron, which is in the D orbit, then L1 will be equal to 1. Sorry, L1 equal to 2, and S1 here equal to half. I will take this as 2 for the D orbit. I will take this 2. So L2, so I am considering state like PD. Let's consider 2p, some other energy levels. Some D electron. Okay, so let's consider this PD only in this particular case. So PD state. So P is having one electron, D is having one electron. So in that case, second electron is in the D state, D orbit. So L2 is equal to 2, S2 is equal to half. So J2 will be equal to L2 plus or minus S2. That will give me 2 plus or minus half 5 by 2 and 3. Okay. Now if you consider these two sets, so I am having from this I am having J1 equal to 3 by 2, 1 by 2, J2 equal to 5 by 2 and 3 by 2. Now these two coupled together to form the total angular momentum, total J value. So that will be like you have different combination here. For example, if you consider J1 equal to half and J2 equal to 5 by 2 or 3 by 2. So if J1 equal to half, J2 equal to half, this J2 equal to 3 by 2, these two values, then we get capital J will be J1 plus J2 to J1 minus J2. J1 plus J2 to J1 minus J2. So that will give values 3 by 2 plus 1 by 2. And that is 4 by 2 is 2. Then 3 by 2 minus 1 by 2, that is 2 by 2 is 1. Now the second one, that is first one. Second one is J1 can be 3 by 2, or we finish first 1 by 2. So J1 equal to 1 by 2, and J2 is 5 by 2. So in this case, J will be equal to 5 by 2 plus 1 by 2, that is 6 by 2, that is 3, 2. 5 by 2 minus 1 by 2, that is 4 by 2, that is 2. So 3 into 1. And the third one, which will be having J1 equal to 3 by 2, and the same values that J2 as before. So J2 is 3 by 2 first. That will give me J value 3 by 2 plus 3 by 2 is nothing but 3. 2, 3 by 2 minus 3 by 2, that is 0. So 3 to 0, 3 to 1. 0. And the next one is fourth possibility, J1 equal to 3 by 2 and J2 equal to 5 by 2. That will give me 5 by 2 plus 3 by 2, which is nothing but 4. The value equal to 4 because 5 by 2 plus 3 by 2, 8 by 2 is done. So that is 4. And 5 by 2 minus 3 by 2 will be 5 minus 3 is 2, 2 by 2 is 1. So 4 is 3, 2, 1. Copy possibility. Now what will happen in this particular case, which means that you are having PD state initially. So this you are having PD state initially that has been split into different energy level because of JJ coupling. So the first one is they have 4 first. Okay. So this 4, these 4 states, 4 energy levels. These energy levels are first one is 1 by 2, 2 by 2 state, J1 and J2 and so. Then we have 1 by 2, 5 by 2, and 3 by 2, 3 by 2 and 3 by 2, then 3 by 2 and 5 by 2. Now this last one splits into 2, again with 2 energy states, and one is for J equal to 1 and the other one because it is having lowest J value. It is having the lowest, having less than half field states. And then we have this one, which is also it's 2 with the J value equal to what was that? 3. So 2 will come down. Then this one splits into 4. Correspondingly, J equal to 0, 1, 2, 3. Right? And then this one also splits into 4. And we have J value which is equal to 1, 2. So this is what happens when you have that JJ coupling. When your atom is very large in size, then the individual electron orbital angular momentum, spin angular momentum is together to form the J1, that is J values corresponds to each electron. Then those J values couples together to form the total angular momentum of the atom, that is capital J. Okay, so that is happening in this case. Okay, so it will also split the energy levels into different number of energy levels. And if you consider uh, the selection rules for this particular coupling transition between these states after JJ coupling, and that will be delta J1 will be equal to 0 plus or minus 1. And this is same as that of J2 equal to 0. This is small j. And capital J, if you consider, that will be delta 0 plus or minus 1. And here also 0 to 0 is forbidden.